Hi, welcome. I'll be introducing the basics of Fourier analysis and signal processing. Let's start by reviewing the idea of periodic functions. So periodic functions are functions that repeat in time, and here's one of the most basic possible examples. This is f of t equals sine t, and here's its plot. So you can see that the function oscillates and it has the same repeated shape multiple times, and this happens every 2 pi time points. So we say that its period is 2 pi and the frequency of the oscillation is 1 over the period, so 1 over 2 pi. Sine of t starts at 0 here, and we say that the phase offset of this function is 0, and the phase at 0 is 0. So here's another example. In blue, we have the same sine function as before, and then in green, next to it, is f of t equals sine t minus 0.5. So you'll notice that this green curve is just an offset version of the blue curve. So we say that the phase offset of the green function is 0.5, and another property is that its phase at t equals 0 is 0.5. So these are kind of two separate concepts. There's the phase offset from the original curve, and then there's the phase in the cycle that describes the oscillation. So another example, this is cosine t plotted in red. So you'll notice that this starts at 1 instead of 0, but otherwise it looks just like the sine function. And in fact, a cosine is just a sine function that's phase offset by pi over 2. So cosine t equals sine of t plus pi over 2. But in this case, the phase of the cosine is actually starts at 0 and then continues from there. Okay, so another way to express these is using complex notation. This might seem like it's a little trickier to understand at first, but it actually is advantageous for calculations where you might need to integrate or differentiate, because exponentials are so easy to manipulate. So cosine of t is the sum of two exponentials over 2, and then sine of t is the difference of these two exponentials, e to the it minus e to the negative it over 2I. And these both come from Euler's formula, e to the it equals cosine t plus I sine t. The most easy way to demonstrate this is through Taylor expansion. So the derivatives of e to the it actually equal each of the derivatives of this function on this side. And so let's see this plotted. Here in blue, I have the same sine t function, f of t equals sine t as before, and then in magenta, I'm plotting the real part of e to the it. And you'll notice that this looks exactly like a cosine function. Let's try to understand this a little more. So what we're going to do is take the real part of e to the it and the imaginary plot of e to the it and plot them against each other. So this forms a circle in the complex plane. So as kind of t increases, we go around this circle. And if you take the projection onto the real axis or the imaginary axis, this ends up tracing this sinusoidal pattern that you see here. So this is the real axis, and this is the imaginary axis here. And you'll see that these are the same sinusoidal functions that we saw earlier. If we go back to Euler's formula, e to the it equals cosine t plus I sine t, you'll notice that this makes sense with this as well. So there's no I in front of the cosine function. So if you take the cosine term, so if you take the real part, that'll be the cosine, and if you take the imaginary part, that'll be the sine, at least to start. So in a more general way, e to the I omega t plus phi is a wiggle, is a sinusoidal function with frequency omega and phase offset phi. And so we'll use this expression later to describe sinusoidal functions. So let's review. We have f of t equals cosine t plotted here, and this is the same as the real part of e to the it, and this function has a period of 2 pi and a frequency of 1 over 2 pi. Okay, so next we'll move on to a few concepts that you might use for signal processing, which are autocorrelation, cross-correlation, and convolution. Okay, so first the autocorrelation. One question that the autocorrelation can answer is, does a signal seem to be periodic? Let's see how this works. So here I have a cartoon of a signal that is periodic, so it repeats in time. And what we're going to do is we take a second copy of the signal, and then we multiply the two signals by each other and take the sum under the curve. Next, we take one of the signals and offset it by a time, let's call that tau, and we repeat the process. So we multiply the two signals by each other here, and we take the sum under the curve. You'll notice as we keep going, as we move the signals further along, now they're less similar to each other. So the sum, in this case, in the middle, actually ends up negative because the signals are now anticorrelated. And so we keep going until, we reach the length of the signal. But as we reach the length of one period, the signals once again align to each other, and so we can expect this sum to be higher. So if we plot all of these sums as a function of d tau, we expect to see something like this. At the center, d tau equals 0, the sum is the highest. Then it begins to decrease. It becomes negative when the signals are anticorrelated, and when we reach one period, there's another peak. So based on this graph, we can tell that here is the time length of one period. And so we can express the autocorrelation at each time as the integral of f of t times f of t minus tau dt. And we compute this for each point d tau. Let's see an example of this. So again, for our basic f of t equals sine t, here's the function plot. And then at the bottom, we plot the autocorrelation. Here, I compute only for certain time lags, which is why there's points rather than having it be a continuous function. So here I plot a of tau, in the integral of f of t plus tau dt at each point. So at 0, this value is at maximum, then it's at minimum here, and then it reaches another peak here. And this is going to keep going if the sine function is infinite. A little bit of a more practical situation. An autocorrelation can also reveal the refractory period and the rhythmicity if you apply it to a spike train. So here's a typical autocorrelation that you see as a function of different time lags. So first of all, you can see this these peaks here, and these are the repetition time. So you can see these occur around 150 milliseconds, then around 300 milliseconds. So this is the rate at which the spikes like to repeat. But then also you notice that where before we had a correlation of 1 at 0, now we have actually a lower correlation at short time lags. And that's because of the refractory period of self-firing. So the width of this trough at 0 actually tells us something about the refractory period of the spiking. And I just took this from a hippocampus paper published in 2013. Okay, and we can apply the same idea to two signals. So this would be called the cross correlation. So if I take f1 equals sine t and f2 equals cosine t, and I apply the same procedure, I multiply the signals, take the sum under the curve, and then time shift, and then compute this for different lags or different time shifts, I get a curve that looks like this. Notice that this here, it doesn't peak at 0 because the functions aren't best aligned at 0. They're actually best aligned around here at a slight phase lag. So doing this analysis can actually tell us at which offset the correlation is highest between two functions. Okay, and finally, a really related concept is convolution. You'll notice that the expression is very similar, except for there's a minus sign here. So we subtract detail, which effectively turns one of the signals around as you shift it in time across the other signal, and this is mostly historical. So one example where you might use a convolution is to compute an expected signal from an impulse response. So here's an example where this might be applied. This is an impulse response for a calcium signal. You can see it's not just at one time. It rises and then it persists over a certain time. And here is calcium signal recorded from cells and identified events, I guess spikes, that are recorded using electrophysiology at the same time. So if you take these spike times and convolve them with the impulse response, you'll get the expected calcium signal. And the reverse process called deconvolution would try to go the opposite way and to try to figure out the spike times based on the calcium signal you see here. Here's a summary picture which explains each of these techniques. So we have autocorrelation, where you have the same signal, you slide it across each other, and you take the sum under the curves. And this is a typical result, up and down. Cross correlation, two different signals, and a typical result, kind of a combination of both of these signals. And convolution, where one of these signals is turn around and then it's the same process. So you end up with the same shape as a cross correlation but reversed in time. So let's review. We were talking about periodic functions, which are functions that repeat in time. And a really nice way to represent a periodic function with a single frequency is by the exponential of I omega t plus phi, which is a sinusoid with frequency omega. And then we also talked about some ways to analyze signals, including autocorrelation, which is this integral of f of t minus tau dt, and then we take this integral over different time lags. Cross correlation, which we apply to two different functions, and convolution, which mathematically is very similar to cross correlation, except for the direction of one of the signals is flipped. Okay, so moving on. Periodic signals aren't necessarily just simple sinusoids, but we can represent more complex signals as sums of sines and cosines. So here I plot f of t equals cosine 2 pi t plus 1/2 cosine 4 pi t. So here is the frequency of the first signal, has frequency 1, and the second signal has frequency 2. So in the plot, you might see these as the slow frequency of 1 and the faster frequency of 2. and then the coefficients in front of these cosines are their amplitude. So here the bigger signal will have amplitude 1 and the smaller signal has amplitude 1/2. Let's try to extend this idea to a slightly more general form. So now we have the sum over all the frequencies that we consider, and a coefficient, an amplitude coefficient at each frequency, and here a cosine and a sine for each frequency f. So this expression can be used to represent many functions if you have enough frequency components, and adding more terms at higher frequencies gives a better result. So a Fourier transform is going to figure out these coefficients a and b for each frequency so that we know what the frequency components at each signal are. Okay, so here's an example. This triangle wave is the initial function that we're trying to represent, and on top of it here is a Fourier series representation using 3 terms. So you can see it does okay, but it's not great. The Fourier series with 7 terms does a little bit better, and then by the time you get to 41 terms, the representation is almost perfect. So the Fourier series actually form a basis set, so it can give a complete description of the signal with enough terms. And as you learned about last week in your linear algebra lecture, there's some mathematical techniques that you can use in order to figure out the coefficients on basically your basis function. And you can also go back to the original function. Okay, and so I introduced the complex notation before, and this is where it comes in handy. This is a much better way to write this expression. Instead of cosine t and sine t, we replace these with exponential of it, and this is the expression we come up with. You see it's a lot more compact, but the form is the same. So we have the sum over all frequencies from omega 1 to omega max. We have a coefficient at each frequency, and here's the frequency omega, which is defined as 2 pi f. Okay, and the Fourier transform, here from this expression, we have a function that represents the coefficient at each frequency. So we go from the original function, f of t here, to f of omega, a function of frequency. And this is the expression for the transform, so integral of f of t exponential of negative I omega t dt. And I won't explain the math going to here, but basically the calculation is performed just like for any other basis set. We take the product at each frequency with the original function and integrate over all time. So now with this transform, we have the signal as a function of frequency instead of as a function of time. And in some cases, let's look at the cases where this might be advantageous. Okay, but first let's review the definitions. So we have omega, the frequency, equals 2 pi f. This is sometimes called the angular frequency. We have e to the I omega t is a sinusoid with frequency omega. And then the Fourier transform, we start with the signal as a function of time, the original, and we transform it to the signal as a function of frequency, f of omega. The Fourier transform, as we've established, expresses a signal in terms of a Fourier series. So that means as a sum of these sinusoidal functions with certain frequencies, and we calculate the amplitude coefficients for each of these signals, and thereby we get a function as a function of frequency rather than as a function of time, which is what we started from. The algorithm to do this is called a FFT, fast Fourier transform, and so that's what most functions in MATLAB or whatever software you'll be using will be called, so FFT rather than Fourier transform. And so next we're going to look at a few examples, and keep in mind that the result from the FFT can be decomposed into real and imaginary parts. And we often look at the amplitude, which is the sum of the squares of these. So this becomes a real number. And I'll explain a little bit more about that in the next few slides. Okay, so here are some examples. We've been looking at sines and cosines, so let's start with those. This is a sine signal, and this is the real component of its Fourier transform. You can see that it's 0, and the imaginary component, and this is the amplitude, which is the sum of squares of each of these. So first of all, notice that the imaginary component is non-zero and the real component is 0, and if you recall Euler's formula from before, the sine has mostly an imaginary component. And then notice also that it's symmetrical around 0 here in frequency, so this axis is frequency, and that's because the FFT gives us kind of two sides, a negative and a positive, and really we're just interested in the positive part. And so the bottom part, this is a cosine, which starts at 1 here where time equals 0, and the real component now is non-zero for the cosine, but it looks just the same as for the sine, as the imaginary part for the sine, and the imaginary part is now 0, and the amplitude looks identical, so we just have a peak in both of these cases corresponding to the frequency of our oscillation. Okay, some more complicated examples. This is a square pulse here, and the real and imaginary components of this, of the time signal, and the amplitude you can see kind of has these jumps and a peak at the 0 frequency, and so this is because you need a lot of high frequency components to describe this square pulse. And another example, a step followed by a decaying exponential looks like a nice smooth function in amplitude, but notice now that the imaginary component is non-zero. And here are the final two examples that I'll show in this slideshow. This signal is a Gaussian, and you can see here it's real component of the Fourier transform and the imaginary component, and you'll notice that the amplitude actually also looks like a Gaussian, and that's because it is. So the Fourier transform of a Gaussian is actually also a Gaussian with a slightly different mean and standard deviation. And then here is an impulse. So this function is 1 at time 0 and nowhere else. And you can see that its real part of the Fourier transform goes kind of crazy. It oscillates, and the imaginary part of 0 is 0. And the amplitude now is at 1 throughout all frequencies. And so you can understand this as when the signal is so well defined in time, it has no peaks in the frequency at all. You can also think of the impulse as a Gaussian with infinitely small standard deviation. So you can imagine that these spectra become the bottom, the same as the bottom part at an infinitely thin width. Okay, so let's move on to some more real looking signals. So as I mentioned before, what we usually plot from the Fourier transform is the power spectral density, also called the spectrum. And so this is basically the amplitudes of the coefficients for each frequency in the Fourier series. So here's two examples. This is the waveform of a flute. You can see it's mostly one low dominant frequency with a few wiggles, and the spectrum reflects that. This is discrete spectrum in this case, but so you can see that there's strong low frequency components and a few higher frequency components. In contrast, this is the waveform of a bassoon, which has a more rich sound, and the spectrum reflects that in that there's more high frequency components and the sound is much more evenly distributed between, the power is much more evenly distributed between. In real signals, what we usually are going to look at is a continuous spectrum, and so this is the square or amplitude of f of omega, and again also called the power spectral density. And so here's a typical example. This is the spectrum of recordings in the hippocampus, and in the paper that I drew this from, they were comparing the power in certain frequencies in different conditions. So here's resting, during a lever press, during feeding, and it looks a little different because it's plotted on a log-log scale, and that's typical for real data. You have to plot it on a log-log scale in order to be able to see anything. And you can see that this peak here around 10 hertz, 8 to 10 hertz, clearly increases, and you'd be really hard pressed to see that in the original signal. Okay, another thing to note is that there are some techniques for smoothing spectra and for calculating error bars. One technique is known as tapers, which is an optimized way to split the signal into many different components. So just imagine these as little segments of the signal that are then averaged and resampled in order to figure out the confidence intervals. And this makes the spectrum look much nicer. Chronix Toolbox in MATLAB is a very nice implementation of tapers. So here's an example of that. This is a LFP signal shown in time, and at the bottom here is the power spectrum, and in black is calculated over this whole time just as a single segment. You can see it doesn't look that great. It's very choppy. And then in red over the same signal is an averaged smoothed spectrum. So you can see it's much nicer. You can start to see the peaks in the signal. Oh. So far we've been talking about calculating spectra for signals over all time that the signal was collected. And this assumes that there has been no change during the data collection time period in the spectral components. So this is often not the case. And what can we do when we know that the signal is changing over time? Okay, well, one option is to display this as a spectrogram. And here's an illustration of what a spectrogram is. Basically, you take the spectrum of the signal, rotate it, and then express it as a color scale instead of this amplitude on the y-axis. And you do this for small segments of the signal, maybe 1 second, maybe less, depending on the rate of change. And so here's a typical example for a bird song. The frequency is on the y-axis here, and then the amplitude at each frequency is shown in the color. So you can see that the song is changing over time, and these bands here indicate certain frequencies. So these are usually harmonics of each other. So this here has a strong component at 3 kilohertz. So that'll probably be the dominant sound that you can hear at that time. Okay, and then finally I want to go over some important considerations for data collection that we can think about in terms of frequencies. Okay, so the two important sampling frequencies that you need to know are the Rayleigh frequency, which is 1 over the total time of data collected, and this is the minimum possible frequency to resolve. This should be fairly intuitive. You can't resolve frequencies that are slower than the time that you've collected. And then the second is the Nyquist frequency, which is double the sampling frequency. And this is the maximum possible frequency that you can resolve. So if you want to resolve a signal that is 5 hertz, your sampling rate needs to be at least 10 hertz. That was it for this lecture, and just to review for the problem set and quiz this week, we'll cover and review the idea of spectra, spectrograms, autocorrelation, cross-correlation, and convolution, and a bit about sampling frequencies, so the Rayleigh and Nyquist frequency as the limiting frequencies in the sample.